Hello everyone, my name is Adin Poljak, and together with my two friends Ahmed and Adna, we made a project from Embedded Systems called Simulation of Transformer Protection. So what our project is about? So we try to simulate different sensor inputs and a corresponding output to those sensors. So for example, what will happen if a temperature, for example, increases too much or pressure or whatever. So that's roughly what our project is about. So in the next video presentation, I will explain better in detail what happens. So first of all, we'll start with two pictures, like how the system looks. I drew these pictures so it's easier to explain. So on the first picture, as you can see, we have a Raspberry Pi, 6 relays, power supply is set to roughly 20 volts, and a Siprotec device. So what happens? As said, we try to simulate different sensor inputs. We don't have real sensors. We simulate them by clicking on a graphical user interface on a Raspberry Pi. I'll show you the graphical user interface later. So what happens when we press, for example, to simulate a critical temperature increase, Raspberry Pi sends a signal to the relays, and the relays trip on the output side. As you can see, it says normally open circuit. The output side of the relays is open, so no current can flow. And when the Raspberry Pi trips, the relays close and allow current to flow. And when that happens, the Siprotec device receives the 20 volt signals, and that's like a warning to Siprotec. Oh, look, something happened there. I need to take action. And that's how the Siprotec device knows when to trip. And there's the same logic for the next 5 other relays. So on the protection side, as you can see, we have 3 single-phase transformer Y to Y connected. They then make a single 3-phase transformer. And because we have 3 phases on both sides, we need to break all these 3 phases with a circuit breaker. So that's why we need 6 single phase or 2 3-phase circuit breakers. In our case, again, we use relays for that. In real world applications, we couldn't use relays because the currents were too high and the relays cannot trip such high currents. They would break, burn, or whatever. But in our case, it worked. So as you can see, we have again a 5 volt DC supply because relays operate on 5 volts. We didn't need that on the image before because Raspberry Pi can supply 5 volts itself. So, but now where the relays are standalone, we need a 5 volt DC supply. The 5 volt DC supply is connected to the relays and to the Siprotec device. And from the Siprotec device, there's an output again connected to all the relays. And what happens when the Siprotec needs to do something to trip those relays? It closes its circuit because in this case, the Siprotec device is just like a giant smart switch. And so when the Siprotec device closes its circuit, a current can flow from the power supply to all those relays. And when the current starts flowing, the relays open. So here in this case, the relays are all normally closed. But when a tripping action occurs, the relays become open, not allowing any current to flow on the output side. In this case, preventing the current to flow and to cause more damage and such, effectively stopping the transformer. That's what we tried to simulate in our case. So we do not take any real measurements. We just use the logic, the binary input-output logic of the Siprotec device. So as said, I'm going to show you the graphical user interface and how it's made. So this is our project in Qt. I cannot run that and compile it because I don't have wiring Pi installed. I don't have the library installed to access different GPIOs on the Raspberry Pi. On my PC, I have that on the Raspberry Pi, but it will be too slow to share the screen from Raspberry Pi. That's why I did it on my PC. I just run it. I just open it in Qt. So first of all, we have the dialog H file. For some reason, our project is called dialog. I do not know why I didn't name it. Here we include everything that we are going to use. So we have included the crypt H and the wiring Pi H. Those 2 libraries need to be included for all the wiring Pi to run and to able to access different GPIOs. This dialog class, just we have our constructor, destructor, and we have our private slots, which are our push buttons, like just like the declaration of it and the user interface declaration. Then we have dialog CPP. This is like the main part where we add functions to our buttons. So first of all, we include the header files, and then we declared like the pins that are used for the different GPIOs, and we made an array of pin states. That's because we want to be able to turn the button on and off by just clicking edit 2 times. Here we set our labels above, which where on and off will be displayed. In the first case, we set it to red, which means off, because when we just start the program, everything is off. So again, here we have our push buttons. Like this is the first push button. As we can see, if the state is 0, it means the push button is off. Then after clicking it, it turns on, so it turns high, it sends a signal, and then the label above it changes text to on, and the background changes to green. Else, if it's already on and we click it again, it turns the digital write to low. It means it turns off the output from the Raspberry Pi and turns the pin state to 0, sets the text to off, and sets the background to red. That happens for the next, again, 5 push buttons. And then last push button deactivates everything. It's a turn all off button. And here we can see for like the pin states for the array. As you can see here for the array state, it turns everything off. It means it assigns every member of the pin state array to 0 and turns digital write everything to low, which means it turns everything off. And turns and also sets the text to off and all the background to red, and it displays a message box off, meaning everything is turned off. Now for the main CPP, here we again include our header file and we include the Q application. In the main, we just set the wiring pi setup, which means like setting up the library and declaring the pin most output. And then we just ran our dialog W, which means like this is like our file, our project. We compile it and run it and return a console application. And for the dialog UI, we use the built-in design tool, even though it's not recommended to use because of future-proofing your project. In our case, it's really simple with just 6-7 push buttons. That's why we use it. And that's basically it for the UI. And let's continue on with our presentation then. So here we have a small video about how it actually works. As you can see on the output side, we have an oscilloscope. I'll mark it with an arrow. We have the Siprotec device. We have down the transformers, the relays for the input and the relays for the circuit breakers. As you can see on the top right corner, there's also another video screen and they are synced. As you can see what buttons are pressed on the graphical user interface on the Raspberry Pi. So as you can see on the oscilloscope, for now we have a signal, we have a sine wave, 50 Hertz. There's the signal from an auto transformer. That means that there is voltage on the output side or low voltage side of the transformer. And when we press the first push button, the temperature trip, as you can see now the output from the oscilloscope is just a straight line, which means there is no more voltage there. So there is no voltage signal. The signal cannot pass because the circuit is opened. And when we again close the push button, turn it off, there is, as you can see, there is now voltage because the relays return to their initial normally closed position. Again, same thing happens for pressure trip. And after that, we have 2 alarms, a temperature alarm and a pressure alarm. They do not trip. They're just like a warning, like, hey, the temperature increased a bit. Someone should go and check it out. So these are those 2. The number 5 is acknowledge. That means that another Siprotec device in the area nearby tripped, because usually Siprotec devices communicate between each other. And that means that our device shouldn't take any action. So when that happens, you can just click and everything, it won't do anything. So this is like a override button. It just disables like the entire graphical user interface. You cannot trip or do anything. The number 6 switch is maintenance. By pressing that maintenance, we open the disconnector switches, which are opened after there is no current in the circuit, so the circuit can be safe for workers to access, so nobody will accidentally restore back like the current to the circuit when disconnectors are opened. So, but in our case, it's just like a flashing LED light noticing everyone that there is maintenance, because we didn't want to put 6 extra more relays in the circuit. And that's basically it for our presentation. I hope you liked it. You can watch the video till the end. And thanks everyone for your attention, and hoping to see you again next time in another video presentation.